Hi everyone. I hope all is well and that you guys are keeping up to date with the content. Now, I'm going to assume that is the case and that you are managing with things since there hasn't been many questions during our tuts or labs, which means I should assume that I won't be getting a ton of emails, say next week Thursday when your first tut is due. Nor should I get anything that Sunday with regards to say the lab. But I guess we shall see. Now today we are going to be looking at finishing our processes or finishing how virtualization happens for the CPU and processes and stuff like that. But firstly, just a quick recap on what we looked at last week. And that was, well, learning about the kernel, which was that operating system process, essentially, that is loaded into memory. We looked at process abstraction, so how a process goes from code to actually something that is executable and can be processed in the CPU. We looked at the PCB, which was that structure within the kernel that stored information on all the different processes currently in memory. We looked at dual mode operation, and that was this idea of our kernel and user mode, where we allowed different functions or different things to be done in different modes. So there was those privileged instructions where that could only be done in, say, kernel mode. And we looked at the events that cause mode transfer and how this mode transfer is handled. So just on those lines of the recap, I just wanted to go through a quick summary to demonstrate once again how interrupts are processed or the flow of what happens during an interrupt. So during normal operations, obviously you have instructions being loaded from memory and processed over and over and over again. And this is obviously running in user mode. And then some interrupts will occur that will then need to be handled. And we spoke about how, well, okay, we need to save the state to the CPU, and this save state needs to be stored in the operating or the kernel stack, and specifically it's stored in the PCB in a region which was set up specifically for, say, this process. And thirdly, obviously the mode would change to kernel mode, and all three of these things happened at the exact same time. And then the interrupt would be processed and handled, whatever it was, and the cycle basically would revert. So that save state would be loaded from the PCB back into, or the save states, all those registered would be saved or reloaded back into the CPU. And then our mode would once again change back to user mode, and the process could then pick up where it left off, or the processing of that process could be picked up back where it left off, like I said there. Now the question that remains is, well, how do we actually implement this mode transfer in a safe way, right? Because care needs to be taken when implementing mode transfer to ensure that there is no potential for, say, a malicious program gaining access to the kernel or gaining access to any unauthorized memory locations or any unauthorized information. So in order to do this, when we implement in safe mode transfer, we need to consider three things, and the first being limited entry. So when we want to transfer control to the kernel, the hardware must ensure that the entry point to the kernel is one that is set up by the kernel. There should not be this potential for a user level process being able to transfer into kernel mode in an unauthorized fashion. Now, for example, the kernel code for handling like the read file system call, so if you want to like read a file from memory, This system call first checks whether the user program has permissions to do so. And if not, the kernel will return an error. Now, without these limited access points into the kernel, a malicious program could, say, jump into unauthorized memory. So without these limited entry points. Now, the second one is atomic changes. So I briefly discussed this a little bit last week, where we spoke about those 3 operations all happening at the same time. So here, changing of the program counter, mode, stack, and memory protection are all changed at the exact same time. And once again, this is because if we change the mode first, for example, then did the other operations, this would allow for a brief time where other events could occur whereby user processes now have kernel privileges and are able to manipulate registers before they are stored in the PCB. Now, this is a specific case when we're looking at multi-processor systems, where this becomes an actual problem, and I'll elaborate on that as we go. And the third part is it needs to be transparent, or it needs to ensure that there's a transparent and restartable execution. So this is the idea that a program should pick up where it left off, as if nothing had happened, as if no interrupts had occurred. The idea here, interrupts should be invisible to the user process. Okay, so just a little bit of what we talked about last week. So on an interrupt, the processor saves its current state to memory, and it changes to the kernel mode and jumps to the relevant exception or interrupt handler. So if you remember last week, we had this slide here, and I ran through the process of what is happening when, say, like a system call occurs. We spoke about the trap table, which indicated, which stored the different handlers. And we had this hardware component that essentially pointed to the relevant handler. So it was like a register that stored the address of the relevant handler. Now, this is somewhat of a simplification, and today I'm going to expand upon these 2 components. And it modifies this diagram a little bit here in the sense that we have this additional processor register, and this was that hardware component that I was alluding to last week. And this register points to what we call the interrupt vector table. And this is essentially like the trap table. Now, this interrupt vector table has addresses to all the various different interrupt handlers, or it's basically a table of pointers to interrupt handlers. And this processor register will point to obviously a specific one. So it will have the address of one of these specific handlers that it should be handling. So if it was, say, a timer interrupt, well, this processor register will store the address of basically the first line of the code for the timer interrupt handler. And all of these are stored with what we call this interrupt vector table. So just to expand upon this, the processor has a special register that in the event of an interrupt points to the corresponding interrupt handler. So this is this register that I was referring to. The handlers themselves are found in a special part of the kernel stack, memory called the interrupt vector table. Again, that's what I was talking about. Again, exactly the same as what I was referring to when I spoke about trap handler, or trap table, sorry. And the format of this vector is processor specific. So in the x86 architecture, very, very common architecture, it's set up like this. So the first 32 addresses, or first 32 entries in the table, are related to exception handlers. and the next 32 to 255, or address 32 to 255, are all interrupt handlers. Now, since the hardware determines which device caused the exception, the hardware will be able to use the correct handler. So here, maybe if there was a mouse input or some sort of input output, because the mouse generated that interrupt, obviously it knows which handler is associated with that hardware device, so it can point to the correct handler. So here, like if there was some keystroke or input output that occurred, this process register would point to that specific handler. If it was like a timer interrupt that occurred, once again, the timer interrupt is a hardware clock, basically. Now that will cause the interrupt, and because that caused the interrupt, this process register will therefore know, okay, I need to point to that timer interrupt. And another thing that we kind of glossed over when handling interrupts was, sure, the process is temporarily stored in the kernel stack or on the kernel stack, but how do we even know where that is anyway? Like, how does the hardware, or how does the CPU know where the top of that stack is, or where this the save state was stored? Well, yet again, we have another hardware solution to this, and once again, it's in the form of another register. So here you can see there is that other register, and this basically stores the address or the location of that saved state. So we'll have that the state of the process is saved somewhere in the PCB of that process. This register will then store the address of that place in the PCB. This is so that when we want to reload that old process that was like halted or interrupted, we then just simply look at this address in this register here and then can load that information from that location. So how does this change our general thinking in terms of, say, interrupt handling? Well, we have some interrupt or exception or system call occurring. Just like before, the process is halted. Now, the stack pointer is set to the base of the kernel stack, and our hardware then saves or pushes the process register to the interrupt stack in the kernel. Control is then switched over to the kernel. The kernel does its job in handling the event, and then when returning from the interrupt, the saved registers are then loaded using that address that we stored in the CPU, and then the process continues from where it left off. So now, a question that you might be asking is, well, why not just store the saved state on the process stack? Why do we store it on the kernel stack? And there are two reasons for this. The first being reliability. Now, the process's user level stack might be invalid due to some bug or some corruption or some error, and you wouldn't want to then have a temporarily saved state in this non-reliable form of, or this non-reliable stack. And then the second component is security. So in a multiprocessing sense, other threads running the same process could modify user memory during a system call. So you would save the state in like a user stack, but then another thread hypothetically could then manipulate the information within that stack because it's at the same privilege level. They're both user programs working with that same user stack. And then this could allow for some manipulation or malicious intent to be able to be achieved. Okay, so this is now basically the overall picture that you get in terms of the interrupt stack. Okay, so we have a couple different registers. one that stores the location of where the save state is, and one that now also stores the address of whichever handler is processing the particular interrupt. Okay, so now another question is, well, what happens when we have multiple processes? So how can the kernel handle, say, simultaneous system calls and exceptions across multiple processes? Now, for each processor, the kernel allocates a separate region of memory as the processor's interrupt stack. So now in our kernel stack, we basically have a separation between processor 1 and processor 2. So how do we handle multiple processes? Well, we just keep them separate in separate regions of the stack. So then save states regarding processes being processed on processor 1 will obviously be saved in the processor 1's stack, within a PCB within that stack. Okay. Now, that is definitely a solution that operating systems use, but most operating system kernels go like one step even further. And instead of allocating a stack per processor, they allocate a stack per process. So an interrupt stack per process or user process. Now, allocating a kernel stack per process makes it easier to switch between the processes themselves. So a switch in this case would look something like this. So if you want to switch between A to B, you obviously stop processing A, store a pointer to process A's kernel stack in the PCB, save states of the CPU in a kernel stack A, clear the registers, then read process B's kernel stack pointer found in the PCB, and then load the state of the kernel stack B into the CPU and then process B's instructions. So the idea here is that we have our PCB, which stores information on all the different processes. And then we have an interrupt stack for process A, for process B, and if there's process C, then process C as well. And this is how we now separate different processes. Okay, so this is kind of how it would look like hypothetically if, say, a process is running on the processor in user mode. So we'll have our kernel stack will be empty because there's been no interrupts and no need for the kernel to get involved. And it would currently be ready for an interrupt to occur. Now our user stack would obviously contain all the information regarding a particular process or some code or whatever. And hypothetically here I've generated some code that could match this representation in the user stack. So when this code is processed, obviously you would start at main. Inside main, then it would call method 1. So when we start at main, it would obviously push the main onto the user stack. Then when method 1 would be called, it would push method 1 onto the user stack. We would then go into method 1. We see in method 1, well, there's another method that's called, so method 2 would be pushed, and then something would be done. In this case, it would just print the word nothing. So this is kind of how it would look like, hypothetically, if this process was running. Now, if the process is ready to run on the processor, but it is waiting its turn, so it's ready to run, but something else is currently being processed. So here in this case, well, the kernel stack would contain the registers and the state to be restored. So this is hypothetically, well, this process was running or was interrupted and pushed out and is currently waiting to be run. So this is what it would look like. So once again, our user stack looks the same as before, but our kernel stack now has that saved state. And this is the kernel stack or the interrupt stack specific to this particular process. So say this is process A, this would be what the interrupt stack for process A would look like. Now, if the process is running on the processor in kernel mode, due to some interrupt or system call, we have this type of representation now. So the kernel stack would be in use. The saved registers and saved states of the suspended CPU would be also in the kernel stack. And the current states of the kernel handler. So this interrupt handler. So the idea here is that an interrupt occurs, we push the save states onto the kernel stack, all right? And then we push the interrupt handler onto the kernel stack as well, so that it can then be processed, okay? It will then be finished. After it's finished processing, it will be then popped off, and then the CPU state will be then reloaded so that the process can continue running just as it was before. And for example, if that interrupt was like an IO event, so I've changed the program here a little bit so that method 2 basically asks the user to input some character, and it will just wait until that happens. So our user stack has changed a little bit. So obviously main would be pushed, method 1 would be pushed, method 2 would be pushed, and then inside method 2, when we call the scanf, that obviously results in a system call, okay? And the system call is specific to like input and output, and therefore would obviously result in an interrupt occurring. And now our kernel stack, once again, after the interrupt, the save states of the CPU needs to be stored, and that's why you see it there. The user CPU state is pushed onto the kernel stack. The system call handler would then be pushed onto the kernel stack, and this is specific to whatever type of system call. And within the system call handler, obviously this is just another program that needs to be run that handles these types of interrupts, and that would then be specifically, in this case, an IO or an input-output driver. And then once that would say this input-output driver was processed, then this would be popped off. The system call would then return, and then this would be popped off. The user CPU state would then obviously then be restored so that the process could be basically restarted or continue from where it left off. And then the system call would be popped because obviously that line has now been executed and method 2 will continue. In this case, there is nothing after method 2, so that would be popped. Method 1 has nothing, so that would be popped. Main has a return 0, so it would return 0 and then pop off. And basically the user stack would be empty in that case, and the process would be finished execution. So the next topic we're going to be looking at is interrupt masking. And that's basically, well, can we interrupt the interrupted? So during the processing of some interrupt, can another interrupt occur? And the answer to this is, well, yes, since interrupts happen asynchronously. And now this could cause some confusion. Now to simplify this problem, the kernel design provides a privileged instruction. This instruction temporarily defers deliveries of interrupts. And on the x86 infrastructure, this instruction is called the disables interrupts instruction. Now it's important to note that these interrupts are deferred, not ignored. So once the corresponding enable interrupts instruction is executed, any pending or previously deferred interrupts are then delivered. Okay, so well, when we're handling interrupts, all other interrupts are deferred. Okay, so what happens though when multiple interrupts occur when disabled? Which one do I process? Do I ignore some? What happens? Well, all these deferred interrupts are stored in a buffer, and they're delivered in turn when interrupts are re-enabled. So they're basically stored in a queue-like structure. So it's first in, first out. But there's only limited buffering for interrupts. And that is because while some interrupts are lost if disabled too long, they become unimportant. And generally, there's only one buffer for each, generally we only buffer one of each type of interrupt. So if a timer interrupt occurs, and then before that timer interrupt is processed, another one occurs, well, we only really keep one of those. Now, how do we prevent the same instruction from causing an exception? So if a handler returns back the instruction that caused the exception, well, then the exception would just immediately reoccur. Well, how do we handle this problem? Well, to prevent this like infinite loop, the exception handler modifies the program counter, which is stored at the base of the stack, to point to the instruction immediately after the one which caused the exception. So remember, the program counter stores the instruction that is going to be processed next. So not the instruction that is currently being processed, but the instruction that is going to be processed next. So if we just shift this to be the instruction after the instruction that caused the problem, well, then obviously we won't get this reoccurrence or this infinite loop. Okay, so we're going to now be talking about actual implementation of secure system calls and up calls. Now, a system call is a voluntary mode switch from user to kernel, and it provides the illusion that the operating system kernel is simply like a set of libraries or routines which the user program can call. And some example of these are, say, create a new process, read from the keyboard, read and write from disk, stuff like that, open files. Okay, and we've talked about this a little bit last week, but here we're going to be talking about how they actually are implemented. Now, to implement these system calls requires defining a specific calling convention. So how to name system calls is a big problem. How to pass arguments, which arguments do we allow, which do we not allow, and how do we receive their return values across this user kernel boundary. And another thing you got to consider is once the arguments are in the correct formats, then only can the user level program issue a system call by executing the associated trap instruction to then transfer to the kernel mode. So it's very specifically set up so that it is consistent across all system calls as well as across different platforms. Now, once inside the actual kernel, a handler handles each of these different system calls like we've talked about with respect to that interrupt vector table. And these handlers are implemented in a way that protects the kernel from any errors or attacks. So there have been in the past clever ways of attacking a system via this idea that, well, we can attack the system when it's actually processing system calls. And in order to get around this potential security problem, they designed this idea of stubs. And stubs basically are a bridge that bridges the divide between a user calling a system call and the kernel actually implementing the system call. And a pair of stubs is basically a pair of procedures which mediates between two environments. So it mediates between like the user environment and the kernel environment. So I'm going to just run through an example of what this process looks like. So how like a system call is actually implemented and how it is processed. So we have this diagram here. Well, we have a user level process, which would be like the code that you would write. And a particular instruction within this program is the file open. So we want to obviously open some file. And that is a specific system call that needs to be processed. We then have the user stub and the kernel stub. And these mediate between the user process and the kernel itself. And the kernel itself is actually obviously what handles the operation of the system call, the file open system call. So we need to be able to bridge between these, and that's where those stubs come in. So step one, the user process makes a normal procedure call to a stub that is linked to this specific call. So here we see the file open basically calls this user stub method. Okay. And then step 2, the stub executes the actual trap instruction. So it's not the user process performing the trap instruction or executing the trap instruction. It is the stub, so the go-between. And this transfers control to the kernel trap handler. So once again, like before, it will then go on to the handler. And the trap handler copies and checks its arguments. So here we see that the actual trap instruction is executed. Now, on the kernel stub side of things, the kernel stub calls the kernel implementation of that particular system call to do the operation. And then the code returns to the trap handler, which copies the return value into the user memory. So obviously the kernel performs the operation, and then the cycle feeds its way back. So the handler then returns to the user level at the next instruction in the stub. So it will return to this return value after the trap is processed. And then because this is returning, it basically comes back out into this function here. So into the user level stub, or the user stub, sorry, returns to the user level caller. Now, I did gloss over a little bit of what this guy does, so I'm going to go into that in a little bit more detail. So firstly, the kernel stub has 4 tasks to perform before the kernel can actually do the operation. Okay. Now, the first one is, okay, I need to locate system call arguments. So these are the arguments stored in the user memory, and this is unlike the regular kernel procedure. Now, if the system call has a pointer argument, the stub must check if that address is within the user domain. And then the stub converts it to a physical address that the kernel can safely use. So in summary here, what are we referring to is, look, when we're talking about locate the system call arguments, if I go back quick, here our user stub has this file open arg1, arg2 that have been passed from the user level process, and these are also passed into the kernel stub version, right? Now, it needs to copy these arguments and obviously check their validity. Specifically, it needs to check if the address that we're trying to open, so the file address that we're trying to open, is actually within the user domain. And if it is, well then we can go ahead and continue on to one of the other roles that it needs to perform. So the first step was basically checking if the file was in the correct memory location. Well, the second one is basically validate the parameters. So the kernel must also protect itself against malicious or accidental errors in the format or contents of its arguments. So in the formatting of maybe the file name specifically, stuff like that, as well as other things related to those argument variables that you can pass through. For example, the file may not even exist. Half the file might be stored within the user memory, the correct user memory, and the other half might exceed beyond, so that would obviously cause an error. And if an error occurs in this validation step, this must be returned to the user. If not, well then the kernel can actually perform the operation. The third aspect is it needs to copy before check. So here the kernel copies the system call parameters into its own kernel memory before performing the necessary checks. So it's going to do it within its own memory because it knows that memory is safe. Now, why is this an issue? Well, this is to ensure that the application can't modify the parameters of the stub checks before the parameter is actually used. So you pass an argument, say a file open argument, to the user stub, and then the user stub passes it to the kernel stub. Now, if it simply relied upon the user stub argument variable and didn't copy it across, what could occur is what we call these time of use versus time of check attacks. Now, this happens when we have multiple processes sharing memory, and one process traps into the kernel So it requests to say do a file open with a particular set of arguments. Now these arguments are just variables stored in memory, right? And these variables are stored in shared memory. Now the other process or another process that shares this memory could modify these variables after the user stub has passed it on to the kernel stub. So therefore the kernel stub needs to copy these arguments into its own memory. It knows it's safe there, it knows it can't be changed, and then do the necessary checks. And fourthly, we need to copy back any results. So for the user program to access the results of the system call, say the file itself, the stub must copy back the results of the kernel, so say a pointer specifically to the start of some file. And it needs to copy this result of the kernel back into user memory. So again, the kernel stub must check the address once again, if it is valid. So that is the whole cycle. So sorry, before I continue, that is the whole cycle of how these system calls are actually implemented and processed, right? Start at the user level process. You send your arguments to this user stub, which is like a gatekeeper that can then communicate with the kernel stub. The user stub actually initiates the trap instruction and passes on the arguments to the kernel stub. The kernel stub performs those 4 components, but the first 2 obviously validating the arguments and checking the memory, or checking if the arguments are from user memory. Well, if it passes those checks, well then the kernel can actually handle the specific system call and do this, in this case the file open, after which it can return the result back all the way down the pipeline back to the user level process. And in this case then you'll have a pointer to the start of a file that you opened. Okay, so that's the user stub and kernel stub, or the stubs idea. Moving on, well, that was implementing system calls. Now I'm going to talk about implementing up calls. Now, for many of the same reasons that kernels need interrupt-based event delivery, well, applications can benefit from being told when events that need their immediate attention occur. So this is like user-level interrupts. So we have virtualized the components of the system to provide functionality to user programs, so we can apply the same technique here. So up calls are virtualized interrupts and exceptions. Okay, so whereas interrupts before were basically hardware interrupts, these are like a software version, or a software interrupt, or a virtualized interrupt. Now, what are the uses of up calls? Well, in terms of preemptive user level threads, if we think about that for a little bit, just as an OS runs multiple processes on a single processor, so too can an application run multiple tasks or threads in a process. So up calls are basically the idea here that we can manage between multiple threads, manage the processing between multiple threads. So a user level thread package could use up calls that switch between tasks, stop a runaway task. An example in terms of a web browser terminating a non-responsive embedded script. So you can see these things like switching, stopping, they're exactly the same as what we talked about before when we talk about, like, say, a context switch, starting processes, stopping processes, switching between processes, stuff like that, right? And it's the exact same concept, but now at a user level and in terms of like threads. And we'll be getting into threads a little bit later on, but up calls are heavily involved in terms of thread management. Another case or another use of up calls is asynchronous I/O notification, so input-output notification. So most system calls wait until the operation is completed what happens if the process has other things to do in the meantime? So it is very inefficient to say have a program that just hangs waiting for some specific input when they could actually be performing some other process or performing some other instructions. Now you can utilize an up call to poll the kernel for input-output completion. So what do we mean here? Well, it basically means that an up call can also be used to send a notification to the application when input-output completes or when an input-output signal is received. So instead of hanging now, we could continue doing other things. An up call could occur, which is like a signal telling you that something's occurred. And in this case here, it will tell us that, okay, now we're getting the input outputs, we're getting some user input. So then we can swap back over to processing that side of the program. And then another case is obviously inter-process communication. So most inter-process communication can be handled with system calls. However, what happens when an application needs an instant attention of another? So for example, a debugger needs to send, to suspend, or resume the process. So here we can utilize up calls to notify the process that the debugger wants to suspend it. Okay, so multiple processes communicating with each other. That's the idea here. And another case, so there's quite a few uses, is user level exception handling. So we have described processor exceptions such as divide by zero. But what happens when the application has their own exception handling routines? So up calls are utilized so that the kernel can inform that the application that it must use its own handlers rather than the kernel's handler. So you could implement your own specific handler that is related to a particular exception, and up calls are utilized to indicate the application needs to use those handlers rather than the kernel's handlers. Now, the last use of an up call is basically user level resource allocation. So operating systems, of course, allocate resources. They decide which processor, they decide which process or say which user gets how much memory, how much CPU. But many applications are also resource adaptive themselves. And this means that they're able to optimize their own behavior based on the resources available. And a very good example of this is Java's garbage collector. So the more resources available to, say, Java, the fewer amounts of times the garbage collector is run. And what the garbage collector does is basically it's like a thread or a part of the Java process that cleans any unused memory, or it removes or frees any unused memory specifically related to dynamic allocations that have been made and are no longer in use. So if you say like new linked list and then later on you delete the linked list but you don't free it, then the Java garbage collector will then free it based on how much resources are available. So if your system has a limited amount of resources, the idea here is that the Java garbage collector will be run a lot of times or frequently, and if you have a lot of resources, then it will be run infrequently. Okay, so just some theory now. I know it's been quite a theory-heavy lecture, but it's just some concepts related to up calls that will help you understand how they are implemented. So as you've seen, or as you should have realized, that these virtual interrupts share similarities to the hardware interrupts, right? They have basically all the things in common. They function in a very similar way. They occur for very similar reasons. They're just ones at user level and then the other ones at obviously kernel level or hardware level. Now, some of these similarities are like the types of signals. So in place of hardware exceptions, the kernel defines a limited number of signal types. Okay, so there's a specific number of hardware exceptions, there's a specific number of signal types, which represent upcall types, basically. Handlers. So now, instead of the kernel, or instead of all the different handlers being stored in like the interrupt vector table, each process defines its own handlers for each signal. We have something called a signal stack. So this is going to be important for the slides to come. Now this is a special stack for event handling, and it is similar to the kernel stack, or that interrupt kernel stack that we discussed for system calls. And this is basically where all the information regarding processing of the upcall is pushed and popped from. We also have signal masking, like we had interrupt masking, right? So signals are deferred in the same way as hardware interrupts, by disabling them and then re-enabling them and processing them as they had come in. And with regards to the processor states, well, the kernel copies this processor state onto the signal stack, and that saves the program counter, the stack pointer, and all the other registers. So just like before, when we copied that saved state into the kernel interrupt stack, well, here we're copying it onto what we call in this signal stack. Okay. And now this is like the landscape that we get for upcalls. So because an upcall is a virtualized system call, we're not really going through the kernel anymore, but we're running through the user stack and the user process itself in memory. So this is the state of a user program and signal stack before a Unix signal or upcall has occurred. And these signals behave in a similar fashion to processor exceptions, but at user level. And this is the type of thing I've basically been reiterating over and over again. They are analogous to processor exceptions. So here we have some process that has like functions and methods, etc. And inside the CPU, our program counter is, say, pointing to the specific line, and our stack pointer is pointing to here, okay, hypothetically. All right, you remember in the previous one where I had main, then method 1, then method 2? It's just somewhere in there at the moment, somewhere within that process. Now, this is kind of what the state would look like during a Unix signal or upcall. Now, the signal stack stores the states of the registers at the point when the processor interrupted. So instead of saving everything into the kernel interrupt stack, everything was then saved into the signal stack. So we would save our program counter, for example, that stack pointer, for example, and all the other saved registers. Okay, and now our program counter would then point now to the signal handler, and our stack pointer would point to the top of the signal stack. And we haven't lost any of this information with regards to where we were, because remember that forms part of that saved state, right? Over here. So now we have a picture of what it would look like as a signal processing, as the processing of a signal finishes, or as the signal handler returns. So our program counter would point to like the return instruction here in the signal handler, okay? And I'm missing saved registers. I'll put that back in. Okay, so this is what the state of the landscape or the user program and signal stack would look like as a signal processing finishes. So it hasn't changed much, but this arrow has moved down a little bit, and it's now currently just about to perform the return instruction. So it's going to pop out of this guy, okay? And once this is finished, or we finish handling, then we need to revert back to where we were, right? Where we were in the original process. And that's exactly what happens. So this would be the state of the user program and signal stack after the upcall. So what ends up happening is all the information that was stored in the signal stack, so all those saved registers, gets popped out and reloaded back into the CPU. So now our stack pointer is once again pointing to wherever we were on the user stack. And our program counter is now pointing to wherever we were on that user level process. Okay. So you can see how it functions in exactly the same way as like our hardware level interrupts, but now we're just focusing, or we're only working within our like user level memory or our user process itself. So that is the end of the first half of this lecture. In the second half, we'll be looking at Unix as well as the shell and how Unix handles process management.